Hello, I am Andreas Zeller. I'm the author of the debugging book, and I'm here to present you a new chapter. Start recording right now, and I hope you're all fine. So, with that, welcome to a new course of automated debugging. Last week we started the new project, and before we go into details of that, two important things. First, our examination office has poised me to remind you that you have to register for, that those of you who study computer science and related have to register for all of their lectures via HISPOS, the HISPOS system. And you can still do so until, well, today. Today meaning, I guess, today midnight. And if you haven't done so already, please register for the course such that you can actually properly participate. The second thing is that we made a couple of minor clarifications to the project description. And if you reload the project, you will find these marked with blue and red text within the description. That is number 2 from my side. And that's already all I am having. So last week we were talking about assertions, that is assertions in debugging. And now is a good time for you, if you have any questions on assertions and how to use assertions and whatnot, to actually ask those questions right away. And you can also ask questions, of course, regarding the project or anything. Let's first ask and answer questions before we get to the teaser of the new chapter. So here comes a question from Lord of Change, whoever Lord of Change is. Informatic master students can receive credit points for attending this course. The answer is yes, but not only for attending this course, but actually for fulfilling the course requirements. That is doing all the 4 projects of this course too. But then you get credit points. And this is of course true. This is of course true for computer science master as well as for cybersecurity bachelor and for entrepreneurial cybersecurity master and for whatever other master courses as well as some bachelor courses that we're having. Further questions from anyone? Now's a good chance to actually ask. If I work for industry, I could easily command several hundred euros per hour or something. So just to answer rather obvious questions. So now's your chance today, and only today, now, every Tuesday. You can ask me for free. Let's see how this works. Zero. That's the number of questions I'm having so far. We have a question answer session. Where's that one? Ah, here it goes. But there are no open questions here either. Okay, Konstantin, Johannes, any open questions from the project that we need to discuss, from the forum that we need to discuss, that we need to talk about?
I don't think so. So nope. I think currently we answered all the questions. Konstantin, is that right?
Yes, I would say almost all questions. Posted all the clarification and not only those already in the project description, but some other ones. You find them on the forum. And I think there was just one problem. Oh, now actually I see some other questions, but I will answer them afterwards. There was a problem with the debugger code, I think, but again, we can take this offline.
Yep, just point me privately to whatever errors I made in the code, and then I'll be happy to fix them. As you may have noticed from my feeble attempts at coding, I'm no better than any other programmer as it comes to coding. Actually, I even think that I'm worse than others. or at least I try to be worse than others, because I try to not to be too sophisticated when coding, because code that is too sophisticated has lesser chances of being readable. So if you think occasionally that, hey, Professor Zoller could actually remove a couple of characters here and there, or use this super fancy Python function, whatever is available. And in most cases, this is actually on purpose, because if I use some whatever Python function to do something, you're not going to, you first have to look up what this function does, and then you learn something about Python, which is fun, but you're not supposed to learn something about. But this should be a side effect of you going through the book. You should learn something about debugging. And then if I write whatever, A++, doesn't even work in Python. If I write A+ equals 1, well, that's probably a border case. I still do that. But if I invoke any particular super functions and that allow me to compress whole big blocks into one line, that's not always the best to do for if you want to have your code that is actually readable. Can you please provide more information on his post-registration? I am not cleared about the steps. I don't know how you.
So maybe I can say a word or two about this. I don't know whether you know LSF. So that's basically where you have to register for all the courses. And there is a tab that is called Prüfungsanmeldung. Probably exam registration. I don't know how it's exactly called in English, but you have to click there and you have to look up the course, automated debugging there, and then you can register for the exam. But in our case, it's not a written exam, but it's the projects. But it's still, yeah. All right. Good.
Yeah, that's all I can tell about this, and that's all I know. Hey, cool. Here we go. Okay. Any other questions? It's quite surprising that you have to register so early. That's because, that comes in the chat. That's because it's a lot of change asks. It's quite surprising that you have to register so early. That's because the first project is out at this point. Normally you can, I don't know what the typical registration dates are, but the issue is that, but normally you can still register or unregister until a couple of days before the exam, I think, or a couple of weeks in. I don't know the exact regulations on that. But yes, today is the day. Today is a good day for you to register. Johannes, any comments on that?
Yeah, so usually you can register or unregister for an exam or an examination up until, I think, a week before the examination itself. Mm-hmm. But since we basically already started our examination, it is a bit earlier for this course, of course. Mm-hmm. Yeah, but I think it's good for you, so you could have a look at the first project and then decide whether you want to take the course and whether you want to try this course before actually signing up.
Okay, any further questions up here? Blah, 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 blah. Still checking. No, 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 no. No, 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 no. So if it says registered, so the next question comes from K. Kim. If it says registered on the CISPA side, does that mean that one is registered? And I will be happy to pass this on to Johannes.
No, this only means that you are basically registered with us and that you get the information about the project, but it has to say registered in the LSF. And there you can basically print out all the exams you have registered for, and it has to say there that you are registered for the exam. So this has nothing to do with the CMS itself. Only the LSF is important in that regard. So you have to be registered in both cases, within the CMS as well as the LSF.
Okay. I think, Johannes, how about you write a bit of news just right now, just in case, or update the news as we have it on the webpage, just so this is entirely clear. I can probably get another extension from our examination office, but I'd rather not overload those folks. They're loaded as they are.
Okay, I can do that.
Okay, wonderful. So now let's get to our actual topics. So your assignment for last week was asserting expectations. That is writing assertions and checking program state all along, which is one of the biggest helps in debugging that ever were invented. Any questions or comments about this? Why doesn't just everybody use assertions or whatever? Now's a good time to ask such questions. Who? Get it from the master. No open questions? Okay. Okay, well, if there's no open questions, well, feel free to ask them anytime. Keep in mind that the fourth project in this course is a project where you can do whatever you like. Well, as long as it's a debugger, and you can design a debugger of your own choice. And the topic, of course, of say assertions could be a great starting point for building your own debugger if you have some property and want to monitor this property continuously and make sure everything works well. This could be great. There's we also introduced we also introduced the memory checkers such as Valgrind and address sanitizer, and building such tools, extending such tools for other environments. I hear that some company has quite some success building super fast processes with ARM facilities and putting them into laptops. Well, lo and behold, there's plenty of tools still missing for these. If you can build a simple memory checker for any of such environments, this could be super cool, or any of such processes could be cool too. You could find bugs with it. You could become, well, not exactly rich, but you could find serious bugs with that. That could be fun too. So plenty of inspiration for that. Our topic that is your reading assignment for the next week also is a topic which offers plenty of opportunities to work on, and in which you have plenty of opportunities to extend the state of the art. It's a technique that is super cool, in the first place, and also super cool in the second place. And still, there are so many opportunities in there to absolutely facilitate debugging. And this is statistical debugging. Let me switch, or let me do some magic here, which is all new. And let me switch over. So our chapter that we are going to present today is about statistical debugging. And the idea of statistical debugging is that you can statistically correlate specific events as they occur during executions with the fact that the program fails or not. And I'm going to briefly walk you through what we have there, because the basic idea is pretty simple, and it comes with great visualizations too. So let me switch over here and see whether this works. So you should be able to see statistical debugging here at the top, and you should be able to see me down here at the bottom. Is that correct? Johannes, can you just confirm that you're seeing me here somewhere?
Yeah.
So this is, I should stop talking, Johannes, we can see it. So this should be me here, or me down here. And you should also see the topic up here. Okay, good. See, we're beefing up our capabilities here, one after the other. So, and I hope the lag is not too big. Konstantin, any comments on how well this works?
Well, the overall quality is not that great, especially for the code.
Okay, let me increase the code size here. Is that better now?
Yeah, it's more readable.
More readable, okay. I can make this even bigger, so how about this? Oops. Well, this might be a bit too big, I guess. So Let's stick with this one. Okay, does it work?
Yeah, should be
Okay.
fine.
Okay, let's see how this is going to work. Okay, so the idea of statistical debugging, I'm skipping here through the synopsis and other stuff, is as follows. You go and you collect the information. You collect events that occur during executions. And these events that you collect typically are very simple events, such as a particular line being executed in your code. And this is precisely what we do in here. So we have a collecting function, which is initially nothing. It's abstract, and then we build an extended collector, the coverage collector, which is super simple. What it does is it maintains a set, and you can see the set here. This is the set of coverage, and this is the set of covered lines. And every time we execute a line, we do this again using our tracer mechanism. We simply add the line to the coverage that we've seen. This again is one of the simplest ways ever to collect coverage in a program. If you want to collect something like line coverage in a language like C or C++, whatever, you have to extend the compiler accordingly such that all this information is actually, all the code is actually appropriately instrumented. Then you have to make sure that this information is also written out during program execution, and that it can, and you need special tools to actually convert them back into individual lines. So all these things are very complicated in most other languages. However, they are pretty simple actually, pretty simple in Python, and pretty simple actually is a vast understatement here, because, well, we're only talking about 2 lines of code. One, to initialize the set of lines that was covered, and the second one that simply adds the current line number to this set. What do we do with such a coverage collector? Yeah, it's very simple. We invoke a function. There's actually some magic in there, which is nice. The coverage collector has some magic built in there, such that it also records the in the same style as our debugger class. It also records all the function calls that occur in this with block, in the body of this with block. So we can do with coverage collector as C, and then we invoke a function. And after that, we can invoke this extra function events, which gives us a set of events, in this case, line numbers that occurred during program execution. And here we can now see, well, these are the lines that were executed in the code with this input, which is 1, 2, 3, 4, 6, 7, 9, 11, 13, 14, and 16. Boom. Well, that's not, by itself is not very revealing, but what we can do is we can actually integrate these into a listing of our code. So what we can see now here is the lines that actually were executed with this input. And here we can see that, well, the initialization at the very beginning, this here, all was executed, so far so good. But what we see, what we also see is that particular lines were not executed. For instance, tag equals true, or tag equals false, or quote equals not quote. These were never executed, well, simply because our input, which was, if I recall it right, ABC up here. This is because our input ABC actually did not contain any special characters such as tag beginning, tag end, or quotes. So this is how you can get coverage very simply in a Python program. This, of course, would be cool for a testing course, because the aim in program testing would be to increase coverage to a maximum, and you would now like to invent special techniques that allow you to measure this coverage and to increase the coverage. But for our purposes, we're doing something rather simple. What we want to do is we want to correlate the fact that a particular line was executed or not with the fact that the program passed or not. So in this case, we can see, well, all of these lines were executed and everything went fine. ABC just works fine with remove HTML markup. And this means that we can say, well, all these lines were executed, everything worked fine. Maybe these lines don't have anything to do with the error at all. Okay. So the fun part now comes as we are doing statistical correlations in here. And for this, we introduce again an abstract superclass, which is called Statistical Debugger. And what this class does is it maintains a set of collectors that collect events. And these collectors come in two categories, namely passing runs and failing runs. Okay, and this is how you use them. So you invoke a statistical debugger, you provide the class of events that you want to collect, and then you say, okay, here's a passing run. And well, one downside of this construction is you have to know in advance whether it's going to pass or not. But that's something we're going to set aside. So HBC is an input where we know it passes. And this is an input where we know that it also passes. But the input with double quotes in here is an input that fails. And this is something and this is the old bug that we were having in remove HTML markup, namely that these quotes were stripped from the input, which they shouldn't because they're not part of any HTML tag whatsoever. One neat effect is you don't even need an assertion or a check for whether something passes or fails. You simply assign a label, namely pass or fail, to that particular run. That's even something that humans could do simply by checking this works, this does not work. This works, this does not work. It's a bit tedious, but yep, this is, but you can also work with manual labels. And now you look at all the events, that is all the lines that were executed, and you look at all the events that were, all the lines that were executed in failing runs. And you see, and if you look closely, you can even see that the lines executed in failing runs are different from the ones in passing runs. Okay, so this is something we can, this is a bit long time. This is something we can actually visualize in a table, and we provide a method.event table in order to look into that. So this is our function remove HTML markup, and we have three different inputs. We have ABC, we have ABC with some HTML tags around them, and we do have ABC with quotes. This is the one that fails. So these two ones pass, and the last one fails. Now you look at this event table. You look at it closely. And then you're going to find, oops, there is a line which is only executed in the failing run, or, well, actually, this is a line for which we can say that whenever it is executed, at least in our trial run, the program fails. Well. Could this be possibly a candidate for the failure? And well, let's go a bit backwards here and let's try to find out what this line 12 actually is. So what is line 12? Here we go. Aha. Line 12 happens to be this quote, not quote thingy in here. Could it be that our error has something to do with quotes? Could it be that the error is either in here or is it up here, maybe in the governing condition? Coincidence? I think not. So that gives us some hint already on what's going on in here. But then again, looking at such event tables, tables like these, is still not yet very helpful. In particular, if you imagine that you may be looking at dozens and dozens of runs, and then it actually may become more and more difficult to figure out when and why a program fails. So we extend the statistical debugger to have, in particular, a difference between failing runs and passing runs. And this then allows us to visualize those lines that occur only in failing runs, namely this one. Yeah, it's quote, not quote. It's quite quote. No, it's quite quote, not quote is quite or not quite associated with failure. Pardon the pun. So, and The neat thing comes when you start visualizing those differences. And this goes back to a work by a guy named James Jones, Mary Jean Harold, and the third one was Stasco. Stasco came from visualization. Mary Jean Harold came from testing and debugging, and Jim Jones came from nowhere. Came from nowhere. He was the PhD student of Mary Jean Harold, and those three had a really cool idea, namely to visualize such differences such that it would be easy for programmers to spot them immediately. The first idea they came up with was very simple. They had the idea of simply going, oh, we're going to take the code and we're going to visualize individual lines. We're going to visualize lines with a red background if they were executed only in failing runs. We're giving them a green background if they're executed in passing runs only. And we're going to give them yellow code if they were executed in both passing and failing runs. And this is what they did then. Well, I'm going to assign a particular value of so-called suspiciousness to those lines, either 1 or 0.5 or 0.0, on whether these events happen in passing and failing runs. Beautiful Python. If event in passing and event in failing, then return 0.5. This is more readable than any comment I could actually write. Okay, and here we have three colors, which I happily defined as honeydew, light yellow, and misty rose. If you don't like those colors, feel free to come up with your own. It's pretty obvious on where to change them. And then I'm writing a function, I've implemented a function which actually takes a listing and puts up these colors in the background using some HTML for that. And without further ado, we can directly go into our visualization. And this is what our code with discrete visualization looks like. You see, those lines that are executed both in passing and failing runs now have a bright yellow background. Those that are executed only in the passing runs have a light green background, and the one which more and more stands out as the culprit, get that line, whatever is happening in here, actually comes with a, well, misty rose, which is red, a red background in here. Okay, good. So far so good. We have a culprit here. Everything is fine. Problem, however, is that, well, simply because it's not always easy to absolutely associate the execution of a single line with a failure. It can be that particular pieces of code frequently fail, but not always fail. Okay, so the next thing that Jones and Stasco and Harold came up with was the idea of actually coming up with a different kind of spectrum, namely a continuous spectrum. And a continuous spectrum would then go and assign different color hues to the code. Namely, you would have a continuous spectrum of green to red. In the middle, you'd have yellow. And the more greener a line, the more frequently it would occur only in passing runs. And the redder a line, the more frequently it would occur only in failing runs. And this is something we can very easily implement. And this is the effect that we wanted to show. If there is a line that actually executes a failing run, and here comes the beautiful implementation of both brightness and hue. They also have a strength, the brightness of the color defined in order to show what the statistical support for the visualization is. And oops, it doesn't show. Why doesn't it show? 1 second. Why is it that every time we want to show something that doesn't work? Okay, let me see. Okay. See, I made a change just moments ago, and I thought that this would actually be all perfect for you to see, such that you could see the beautiful, the beauty of visualization. So let me just rerun this whole thing. Here we go. And after a few seconds, we should be able to see, thank you so much. You should be able to see the beautiful color. So this now comes as a spectrum of continuous colors. And now you see that there's green lines and red lines. Yes, and the green lines are strong. They're very green because, well, these only occur in the failing runs. And the red line is very strongly red because it only occurs in the failing run. And even if we now have failing runs, even if we now have runs that execute that culprit line, yet still pass for whatever reasons, then you will find that there is still a highlighting here. You can still get pointed to this line 12 in here because it still has a more reddish hue than the other ones. You do not see the green due to the green screen. That's too bad. 1 second, let me just fix that. That's an interesting fun part here. Okay, why can I see things? That's really fun. In my monitor, now I see what's going on. Okay, thank you so much. So let me just put those lines in which you see the virtual background. These are the lines. So these are the lines with the green screen. Wonderful. So are we better now? Green color. Here we go, green screen. I actually do have a green screen, but that's eliminated at some other point. Okay, so fine now. Thank you so much. Technical difficulties. As I said, it used to be the case that you would have trouble connecting your projector and then dealing with whatever resolution and lighting and whatnot. And today, all of this is replaced now by fancy Zoom connections. Can you hear me? Can I hear you? Can you see me? Oh yes, thank you so much. Okay, good. Let's get back here. Now in full green, you can wonderfully see the lines that are being executed in failing runs, in passing runs only. And the orange lines are those that are executed both in passing and failing runs, with different shades of orange, by the way. And the yellow ones are lines that are executed, well, in both passing and failing runs equivalently. Okay, here's another program. This is the middle program. This is actually the standard example for this kind of thing because it was invented by Jim Jones and Mary Harold and John Stasko to actually show off how their program would work. So this is a program which is supposed to take, which takes 3 numbers, and it's supposed to return the middle one. The middle one is the one that is neither the minimum nor the maximum of these 3 numbers. So if you pass, say, 1, 2, and 3, it's supposed to return 2. So far, so good. Unfortunately, this fails. If you pass 2, 1, and 3, then it returns 1, whereas the middle number of 1, 2, and 3 still is 2. And if we feed a couple of test cases in that, and with these test cases, 3, 3, 5, 1, 2, 3, so these 5 here are all passing, whereas this one is our failing one. And then you can actually look this up. Well, again, we have an event table in here. So far, so good. And here comes the visualization with spectrum. And this is, well, obviously, this is the key example here. Everything works beautifully in here. You see there's different shades of yellow and red and green. And you do have this line, return Y, which is very nicely highlighted. And this is actually a line which is wrong in here because Y is, well, whenever this line gets executed, the program returns a failure. And this is a line that actually has to be fixed. And, well, figure it out for yourself how it has to be fixed. But it's actually not too complicated looking at that. For simple symmetry reasons already, you can find out which possible return value this should be. So, so here's actually a fix. I'm just going to go over that. So this visualization works neatly. The problem, however, is that if you do have a program that consists of thousands of lines of code, you may well end up with hundreds of lines that actually are tainted red. And then, well, that's still neat because it allows you to focus on 10% of your code. But focusing on 10% of your code may not be the optimal way of working because, well, you already may have an idea of where the bug is and maybe this is already 10%. And then simply seeing that these 10% also come in red may not be the optimal solution. What people want, what users want, is a tool that directly pinpoints the line that is to be fixed. Give me the one single line that we want to fix. And so researchers have worked on taking these metrics and create rankings out of them. So why not rank all the lines in my code by suspiciousness? That is, first look at line 6, then look at line 5, then look at line 3, then look at line 4, I guess, then 9, then 10, then 2, then 8, then 12. So simply ranking lines according to their suspiciousness from red to green. Okay, so, and this is what people have done too. And you can then go and create such a ranking. This means simply to sort this list by suspiciousness. And here you will find that line 12 obviously comes at the very beginning because this is the reddest line in our code. And this same thing, of course, also works with the middle code. So 6 comes first, then comes 5, then 3, then 1, then 2. 1 and 2 actually identical, then 4, 8, 9, 10, and 12. Okay, so that's another idea on how this works. And for this, actually, there's another metric. So we have seen Tarantula. Tarantula is this visualization tool. Later, people have come up with better metrics. This is the so-called OKI metric, which actually comes from the biology domain, where a Japanese researcher has used this metric to associate the prevalences of statistically the prevalence of fish in a pond. That was and this from the biology domain has made it into debugging. And this is a simple formula we can also implement. And then we get actually another metric which gives us pretty much the exact same ranking. Slightly different colors, though, if we actually show them, but still the same ranking, and they also point to the same, and they also point to the same error. All these metrics there's been dozens of metrics that have been proposed. Tarantula was the first. OKI in most evaluations turns out as one of the best. All these metrics, however, somewhat intercorrelate with each other. So whatever metric you choose may only be a minor difference, but it also makes, but Tarantula was the first, OKI is the one that shows out to be one of the best. So why not go with one of these OKI metrics? So these visualizations, as we have them over here, I'm not sure whether they have ever been put to the test or whether they ever have been shown to be useful to people. They're certainly cute. That's something one can say. And I am actually very sure that they would be very helpful, not only in programming in the small, but also programming the large. So here's your map of your program. And you want to, and if you have, and whenever you have the choice when examining the program between multiple locations, you want to go and maybe go for those locations first that have a higher suspiciousness. This is, however, not the way that research has evolved. Research has evolved mostly in going into these ranking schemes. Ranking is great because ranking is something that you can evaluate against ranking is something that you can easily evaluate against a ground truth, namely, well, we know where the bug was fixed, so the higher the position of the fix in the ranking, the better. And however, it has shown that giving developers a list of such ranked a list of such ranked locations in the code is not precisely what developers want or what they need, simply because when you are reasoning about what went wrong in a program, you are looking at lines in context, in blocks, and you try to understand how all these lines, how all these locations, how all these functions actually work together. Whereas if I tell you, jump to line 6 in your program, look at that. Is this right or is this wrong? Well, if you told me, look at line 6 in here, whether in order to understand whether this is right or wrong, I first have to understand what the entire function is, and I first have to understand how it's going, how it's supposed to be used, and what it's supposed to return. So simply pointing me to one single isolated location is not going to help me that much. And if I say, well, and even if I find that line 6 is actually correct, and then I get asked, hey, how about line 5 then? This is the next in our list. Ah, line 5, is this correct? Yes, no. Well, if only I knew. Is line 3 correct? Is line 1 correct? Is line 2 correct? And this is a mode of operation that, well, that actually works well for a benchmark. That is when you're comparing against the ground truth and they say, we want to predict the faulty line as well as possible. However, in practice, unless the first 1-2 suggestions here actually pinpoint the location, and there you go, which is great. But if you, as a developer, have to walk down such a ranked list of lines, no, you're going to very quickly lose it, because these locations, this list of locations, simply does not tell you enough about the context of things. So for those of you who want to go a bit further into that, at the end of the chapter, there's a couple of possible extensions in various ways. One interesting thing is that the infrastructure is actually set up to collect arbitrary events, not only whether a line was executed or not, but you can also say, I want to collect all values that I've seen. And that's very easy to do, in particular in Python. So these are all the values that exist at some point during execution in our remove HTML markup function. And then you can go and actually find out, are there particular values that occur only in the failing run? So what we have in here is, for instance, C equals a single quote. Our program fails when, or more precisely, when we have a single quote in our program, the program fails. And we also have the input string, obviously. Well, if this is the input, the program fails. This is not so super helpful at this point, because, well, this is unique for every single run. But we also see quote equals true whenever the program fails. And this could give you an interesting hint on, well, the failure is statistically correlated to the fact that C contains that we have a double quote in the input, and that quote becomes true. So rather than looking into individual lines of code, we look into values of variables, and these can also give us important hints on things that occur only in the failing run. Obviously, well, for quote, there's only 2 values. There's true and false. That's fine. But for more complex bugs, you may want to come up with an abstraction of sorts, such as a set of values that C is in, or a range of things that C is in order to associate these more abstract conditions with failures. But there's clearly potential in here, and that's something that is not nearly enough, and that is not nearly enough investigated. Actually, we can also visualize these again using the Tarantula and Occii metrics, or discrete metrics, and this then shows you these are values that occur. These are values that occur only in the passing run. These are values that occur in both passing and failing runs, and these are values which occur only in the failing runs. And this is again how you can statistically associate specific features found during execution with passing or failing runs. You can actually, if you think further about this, you can actually think, wow, This is actually a machine learning problem. This is a classifying problem. We have a couple of inputs, and we want to determine which features there are that turn a classifier into true or false. Or can we train a classifier to automatically find out those features that actually separate true and false? This is the last thing. This is also something that is very much left unexplored at this point, where the research community is beginning to get into that. But if you want to go for if you want to publish a number of fun academic papers, or if you're looking for a great bachelor thesis or a great master's thesis, come to me. You can what we do here in the last lines here is I pull in a simple machine learner. This is a decision tree learner, and most of the code that we're setting up here is simply to arrange the problem in a way that it can be fed into a learner, and this learner in the end produces a decision tree. And this decision tree, in which we are feeding in lines in here, whether a line was executed or not, tells us at the very end, this is the feature we're having. So we're seeing this 12 in here. This is the line number. And whenever this line number was not executed, that is, its value is negative, then the outcome is pass, meaning that the program will not fail. If, however, line 12 is positive, that is, less than 0 is false. If line 12 was executed, then we have then the program is going to fail. And this is also something that is still open for further exploration. Such a learned machine learning model. This is a very simple one still. Such learned machine learning models can also be used to predict whether an input will cause a program to pass or fail. So if you have a long-running program and you want to make sure, and you have a model for your failures already, you can use such a model as a proxy to implement workarounds. For instance, you can say, okay, and if I can predict that this input is going to fail, maybe we shouldn't invoke this function right away. And all of this interplay between individual inputs and individual outcomes of the program becomes even more interesting when you feed in test generation. That is, you can actually validate those hypotheses as you like. And that's something we're going to explore. That's something we are going to explore in a couple of weeks, not right now. For now, I've given you some material on how to associate events with pass or fail, how to visualize these, how to rank these, and even a bit how to feed these into in a machine learning infrastructure of your choice. So again, there's plenty of opportunities in here to do further research work, implementation work, or project work as you like. This chapter also defines quite a number of classes. We have statistical debugger, we have difference debugger, we have discrete spectrum debugger, continuous spectrum debugger, and ranking debugger, and so on. And you can actually make use of all these debuggers for your own code and then list the code with appropriate colors, and then maybe even use these things to find out which line in your program is it that would be whose execution would be correlated the most with failure. Okay, and then there's also the infrastructure on tracking those events, and this is again something which you can use as you like. So this is all we're having about statistical debugging, and I very much urge you to go through the chapter yourself. As usual, try this out yourself. Try out when the whole thing works and when it doesn't. Try if you have some background in machine learning. Feel free to place this into a machine learning infrastructure of your choice. As I said, plenty of opportunities in here. And I hope, and maybe this can even become the foundation of one of your own freely defined projects. So that's all for today. I hope you enjoyed the chapter. Thank you very much. And I'm happy to take questions. And for this, let me switch back to regular video. Hopefully, well, 1 second. Let me first turn on my green screen again. Otherwise, you're simply going to see the green screen. So here we are. Ah, cool. And we go back to our original camera. Here we are. Ah, the beauties of modern zooming. Okie dokie. So, questions any kind on statistical debugging? No question, no question, no question.
So right now, I don't think there's a question on the lecture itself, but rather on the registration and LSF stuff.
Okay.
However, I don't know whether you've seen the question. It's a master student in language science and technology.
Yep.
And he or she cannot register in the LSF, but I don't think we can answer this. I think you have to go to your examination office and ask them whether you can take that course or not.
Indeed, that's true. Please, dear anonymous attendee, please go to the examination office and check how you can place this course as part of your studies. I will be fully happy to support this. Just let me know what to sign on and whom to write, and I'll be happy to help you with that. Having said that, there's also plenty of opportunities if you work in computational linguistics, because this gives you plenty of concepts, thinking about inputs, thinking about when does my NLP system work as it should, when does it not work as it should, which are the things that I can statistically correlate with that. And again, plenty of opportunities for much better debugging than what we usually have. In particular, then maybe this is the nicest thing about statistical debugging. You can very quickly make use of dozens and hundreds of different runs, some of which may pass, some of which will fail. And this is something which you simply cannot aggregate in a regular debugger session, where you would normally always look at only one value at a time, which takes time. Whereas with statistical debugging, you can actually compress a large number of information into rather simple visualizations and rankings. And yes, that's a real cool thing. Okay, Konstantin, Johannes, any questions left?
Yeah, but again, it's concerning the registration in LSF.
Yep, check with your examination office. They will be happy to help you. We cannot help you with that, I'm afraid. We're only doing the course. we're doing the course. We're giving you the grades, but where these points then go to is up to your examination, is up to your courses of study.
Yeah. So, but if something like that happens and you message your examination office, they usually let you attend the course then.
Yeah.
If you raise the issue before the deadline.
Yes. Raise the issue right now, and everything will be just fine. Okay. Anything else? Then I'd suggest that we go and call this a day. Thank you very much for attending. Next week, we have one highlight. We have one highlight after another because now we are moving from interactive debugging into truly automated debugging, where tools automatically find out error courses. Next week, we're going to look into delta debugging, which is a technique which automatically, in a large input, finds out which small part of this input which small part of this input causes a failure. Super helpful, can tell you. And the week after, we're going to do a similar thing for a piece of code that has changed quite some time that has changed a number of times over time, and which in the past passed, and which now fails. And the question is, which change of the many changes that you or others have made actually caused this behavior? And there's also very nice tools that allow you to go through this history of changes and automatically find out which change it was that introduced the failure at hand. And then I think we'll already be at our holiday break because we only have 2 more lectures to go before we all head off into our Christmas break. And after in the new year, we're going to have 5 more lectures, but that's still some future to go. Okay, no more questions, nothing in chat. Thank you very much. It's been a pleasure, and see all of you next week. And if you have any questions in between, feel free to ask them in the forum again, and we'll put them up. Okay, great. See you, folks. Have a great day. Bye-bye.